Hello, everybody. Welcome back. So if you have your exam redos, please bring them to the front along with the exam extra credit problems if you did them. You can either attach the extra credit problems to the back of the exam, or if you just wanted to turn them in separately, you can do that too. It's fine. I've got a little baby stapler up here if you'd like it. Kind of giving us a little bit of a rundown. So we're in the last week of classes. We have 2 more classes together, including this one. And then technically a third one, but that's going to be the exam. So it's not really going to be any lecture or talking too much, just questions for clarification, stuff like that. So we have 1 quiz left, which is going to be a double quiz. So basically, I'm going to give you it's probably it's going to be 2 separate documents. They might be double-sided, they might be single-sided, like it might just be 2 pages separately. So I'm going to grade it it's going to be 2 quizzes in one. So there's I believe I've already written it on Canvas. If you're looking at the grade book, it says quiz whatever part 1 and quiz whatever part 2. I'm gonna have to kind of delete a few and reevaluate because we didn't get several quizzes because of my sickness and everything. But either way, so that's how it's gonna work. So basically, you're going to take the first quiz and then move on to the second one. I'll give you both at the same time so you can choose whichever one you want to do, and I'll grade both of them. It's going to be a quiz purely on chapter 4, specifically way more emphasis on 4.3 and beyond. So indefinite integrals, fundamental theorem of calculus, integral substitution. That's going to be the core elements of it. Okay. Then we'll take that. I'll post all solutions of everything on Wednesday after class, including the solutions to the quizzes that we just got, because you're not going to get them back. And then I'm also sorry, I forgot to post the review. I just needed a little bit. Granted, all the previous reviews are all good practice tools as well. Like going back over exam review 1, exam review 2 will all be useful study tools, along with exercises and stuff like that. So any question? So then next week on Monday, 9:30, we'll take the exam. It'll be cumulative. I think there's 7 or 10 questions from the department. The good news is, I just found out they're multiple choice. So you basically you're gonna still I'm going to grade. So the department requires it just to be right or wrong, but I will still grade for partial credit. So basically, this is a win-win for you because now your choices are narrowed down to 4 options. So if you're not getting one of the 4 options through your work, you did something wrong and you can go back and correct it. So I'll be recording it for the department based on right or wrong, but that does not affect your grade. Your grade will purely be based like I normally grade things, which is partial credit comes first. Yeah, I guess technically no, based on the department, but I would still recommend writing the work just so that you can get partial credit in case you don't get it right. You know what I mean? And then there's going to be a small, oops. My background. What is that one? It was just a bunch of shapes. And then of course there's this one, which I don't know. I probably shouldn't put this on a recording, but whatever. But anyways, oh no, the people watching the recording can't see that, so that's good. But anyways, to remind me of certain things. Anyways, yeah, and then the final exam will have 7 to 10 or whatever it is questions that will have a multiple choice outcome at the bottom of it. And then the rest of it will be some questions that I've written. It should be still doable within an hour and 50 minutes, just like all of our other exams. So kind of expect the same length. I've taken their questions into account and then added on a few more to make it seem just about as long as the rest of them. So any questions on that? Okay, the next thing I want to talk about, I'm sure you guys have been getting it. I normally mention it earlier in the semester, early, a few weeks before this, but you probably have been getting those emails about course evaluations. Have you been getting those incessant emails? Perfect. I love it. Just a couple things on that front. So if you haven't done the evaluations, it's gonna start getting real aggressive about it. Basically, what happens is every single time you click a new link on your evaluation page, it's gonna say, hey, you need to do your evaluation. It's really annoying. Just let you, do it later. Just let you know, I have no control over that. That is something that CSN makes it do, or the Canvas makes it do. I want to email our IT director a little bit later to see if I can turn that off, if there's a way that I can turn it off, at least for my class, so you don't have to deal with it every single time with my class. But just know it's not personal. I don't have any control over that. So I'm sorry if it's ticking you off. But more to the point. So if you have the time, I know you guys are very, very busy. I don't presume to think that this is the only thing going on in your life, but if you have the time, please fill those things out and give me your honest criticisms, knowing fully well that these things, I don't see them until grades are posted, and it's like 2 or 3 weeks after that. So I won't see your evaluations of my course for about. Excellent question. So it's completely anonymous. So when I get it, it shows me like, it just gives me kind of a histogram of all your choices on like the questions that say like could be good, better, blah, 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 like on a scale of 5. It gives me just a histogram of those things and then the average. And then for the comments section, all it is it just gives me bullet points. And there's no name attached to it. It just says what the person said. Good news is we're in a math course, so I don't know what your writing looks like. So I can't be like, oh, that's definitely something Kate would write. Now I can be angry at her. Whoa. What happened there? Sorry, 1 second. For people watching the recording, okay, there we go. So you can give your honest criticisms, knowing fully well that I will not know, I cannot trace it back to you. I hope by now you understand that I'm not a vindictive person. I'm not evil or whatever. So I'm not gonna even if I could, I can't. But like you don't have to worry about me being malicious or anything like that. What? You like? I mean, you could try. Yeah, I can't. Like, I literally can't. Even if I wanted to, but I don't want to. I want you to give me. I want you guys to give me your. I literally can't even. Exactly right. But I really appreciate when students give me their honest criticisms. It's the only way that I become better as a teacher, because I'm not the one taking the course. I don't see your guys' perspective. So please give me your honest criticisms and ideally I'd like you to do it for all your classes if you have the time, because that's the only way we make CSN a better school, is by having the teachers learn from their mistakes and making their courses better. So give me all your honest criticisms to if you want to, you can even add I know the questions that get asked are kind of vague. I wish they would put more thought into the question topics, but suffice it to say, you can leave me any comments that you want in there. So what I appreciate the most is if you give me as detailed as you can, reasons for your criticisms. As much as I love the comments of like, hey, Phil, you rocked, or Phil, you sucked ass, it doesn't really give me much. Like, what did I do that rocked? What did I do that sucked that ass? What did I do? That doesn't sound right when I say it like that. You're like, ah. There probably were better ways to phrase it, but you guys get what I mean. Did you like the structure? Did you like the exam redos? Do you have any suggestions on how to improve the exam redos? This is my 3rd time doing this exam redo. It's a process that I've been really thinking about and putting a lot of effort into, and trying to tweak it to make it perfect. But there's still plenty of room for improvement. So if you have any suggestions, like maybe you think the due date should be longer, there should be more like scheduled times for outside of class to ask questions about it. those types of things. Those are the things I'm interested in. And they can even be ridiculous requests. And I don't mean that like, ridiculous isn't the right word, but I remember my very first time teaching as a TA, we always had the quizzes in the TA section. And the way we kind of got our own free will in how we ran our recitation sections. And one of the things that I would do is I would always give the quiz at the end of class, and I would leave the rest of the time for like the first 30 minutes for covering the new material, and then like 10 to 15 minutes of doing a review. And one of my students left in the review is like, I don't like that you put a review before the quiz because it discourages me from studying outside of class. Now, did everyone else think I got like several other comments saying that they really appreciated the review. But it gave me something that I had never considered before, of trying to make sure that the review was not as all-encompassing. It's more of a kind of like maybe doing something like that. So those are the things that really stick out to me, is trying to figure out what you guys would like to see in your classroom. I read these after the semester's over and try to incorporate them in my future teaching. So if you have the chance, please fill it out. I am human, so I'd like it to be kind of nice and constructive. But if you really disliked me, that's okay. I can handle it. Just what? Keep it on a separate pile. No, but the main thing, just if you can, even if you are really angry about the course, please try and give me some criticisms to improve it for you, how I could have made it better for you. I really appreciate you guys taking the time to do that. If you don't get around to it, I totally understand, but if you can, please do so. So any questions on that? I am recording. Good. Okay. All right, then let's continue off where we left off. So we're talking about U substitution. So the process kind of seems hand wavy, but especially if you go back to kind of how it works, is basically you choose a U, a choice of U, and then you take the derivative of that with respect to your given variable. So in this case, our given variable is x. So we'll make U equal to x squared plus 1. You take the derivative with respect to x. You get du dx is equal to 2x in this case. And then you do that hand wavy, quote unquote, multiply by dx. And the reason why you do that is that you can solve for dx and replace it in the expression, or replace it in the integral with now an expression that purely deals with du. You'll know you've done the integral substitution correctly if there's no more x's once you've simplified. So notice that once we simplified, we just had the integral of 5u to the 4th du. That is an integral purely in terms, it's integrand, it's purely in terms of u, and the variable of integration is u. So we can just purely work with it, integrate it like normal. 5 comes out front, u to the 5th over 5 plus the constant c. Then you get u to the, canceling the 5s, you get u to the 5th plus c. And then at the very end, only at the very end, will you replace your u back with your original variable. And then we talked about the typical choices. This is not an all-encompassing list, as you guys remember. It doesn't always work out. Your first attempt doesn't always work out. That is why I always recommend using scratch paper on the side. I will always there's always a piece on the very, very back of my exams that is scratch paper, but I will also make sure to bring plenty of extra blank paper in case you want to use some scratch paper. So you don't need to bring it yourself. I will have it for you. But the typical choices, once again, are things inside powers or radicals, like we see in the first case, something in the denominator, sometimes in conjunction with option 1. So like this second example, we didn't make u equal to the entire thing. We just made u into the inside of the denominator. And then the other one is the inside of a function. And I really, really want to stress this to you guys. It is way more like just getting started is the hardest part. Like I know personally for me, the hardest part of writing an essay, I suck at writing essays. I don't suck anymore, but when I first started, it was really, really hard for me to get started. I never knew where to start. Like, how do you start your first paragraph? I got like a lot of anxiety, but eventually it was just like, just write something down. Like that was what that like one of my teachers said, is like, just write something down. You can always edit it. You can always go back and erase what you wrote and rewrite something new after you've gotten your idea down. So writing the first U choice, it might not work out, and that's okay. You just erase it and restart. Why do you think our pencils always have an eraser, right? If we're on, so anyways, just point being is to try and just be okay making the wrong call. This is actually going to be very, very useful to you in your future math courses. If you are planning to move into another math course, the idea of being okay with failure on your first attempt is monumental to your success, because that allows you to say, okay, I didn't get it right this time. I know now for the future that I don't do that. I like to think of it, I think I said it last time, but like basically imagine like U substitution is one of the first toolkits in your mathematical tool belt. And as you become more and more handy, you look at each situation, you're like, that is not going to require a hammer. That's really going to require me using a jigsaw and something else or whatever it is. I'm not a very handy person, so I don't know all the tools. But point being is you start looking at each scenario. The more you practice and are okay with failure, the better you are at saying, this situation is really only going to require this idea. Or I've seen that before. It's a little different, but I know what to do. So please keep that in mind. It's okay to fail and come back to it. So let's do another. Find the following indefinite integral. The integral of 6x squared plus 8x minus 10 over x cubed plus 2x squared minus 5x plus 6. Good choice of U. Take a second. Think about what you would choose. All right, what do you guys think? The denominator, good option. Always a good option. So we're going to let U, and you don't have to say let U. You can just make U equal to x cubed plus 2x squared minus 5x plus 6. Now, technically, there's the middle step of writing du dx equals the derivative, but we're just going to bypass that step and multiply by dx at the same time. So we get that du is equal to 3x squared plus 4x minus 5 dx. And then what I like to do is then I like to solve for dx. Some teachers will not do that. Some textbooks don't do that. And they try and do this thing called term matching, which I think is just unnecessary. But if you like doing the term matching, if you've seen some videos or something like that, and that makes more sense to you, continue to do that. It's still mathematically valid. But I'm going to take this. I'm going to stop drawing this after a little bit. I'm going to stop writing this down in the future, but this just while we're still seeing this in action. So we get that dx is equal to 1 over 3x squared plus 4x minus 5 du. I always put the du at the very end to make sure that it is at the end, because that's where the differential is supposed to be in an integral. It's supposed to be at the end. The dx, the df, the du, whatever it is, always ends up at the end. So, any questions so far? Okay, so then this becomes the integral of 6x squared plus 8x minus 10. Remember, that thing wasn't the u, so it's still in terms of x. And what our hope is with this integral substitution is that that thing cancels. That is our hope. Our hope is that all the x's will go away. Just like in life, right? Ha ha. 1 over 3x squared plus 4x minus 5 du. Oh no, it didn't work. Or did it? You see any connection between 6x squared plus 8x minus 10 and 3x squared plus 4x minus 5?
Take a 2 out of the distributed or back out of 2 from the numerator.
Exactly right. Exactly right. This, if you were to factor out a 2, you get 3x squared plus 4x minus 5. And then this cancels. Sometimes you might have to factor it out from the original portion of it. Sometimes you have to factor it out from the du portion. It could have just as easily been that instead of, like, maybe instead of 3x squared plus 4x minus 5 for your du portion. Maybe we got 12x squared plus 16x minus 20 in the denominator, at which case you would factor out a 2 and 6x squared plus 8x minus 10, and then you would cancel it here. It all depends. I'm mainly mentioning that sometimes you cancel, you factor from the integrand portion. Like sometimes you cancel over here, sometimes you cancel down here. And so now all the x's are gone, and we have this thing purely in terms of u. It's the integral of 2 over u du. Now all the x's are gone. We'll integrate with respect to u. Classic mistake that I've mentioned before is the students will now replace u back with x squared. Don't do that. Only wait until you've integrated. Once you've integrated, then you can replace the u's with x's. So this becomes 2 ln absolute value. Remember, when you have 1 over your variable, the variable, it's natural log of the absolute value. So absolute value of x cubed plus 2x squared minus 5x, or let me write one more step, sorry. 2 ln absolute value of u plus c, which then we can replace with a 2 ln absolute value of x cubed plus 2x squared minus 5x plus 6, absolute value ends, plus a constant c. All right. Any questions on that?
How do you know when to do a natural log versus moving the variable to the numerator with a negative exponent?
So the only situation, oh, okay, yeah, I see what you're saying. So how do we, like, when do we know to, like, if you have 1 over u to the blank, when do we change it to 1, or when do we change it to u to the negative blank?
Yeah.
The only situation where you don't change it is if it's to the first power.
Okay.
Every other situation, no matter what type of fraction or decimal it is, u to the 1 over u to the 1.1, change this to u to the negative 1.1. It is only the case when it is 1 over u, the first power, that you need to worry about the natural log. Every other situation, use that power rule. Great question. Great question. Okay. Anything else? Okay, let's do this next one. Sine squared times cosine, sine squared theta times cosine theta d theta. Take a second. What do you think we should do? What should we make u?
Theta.
I'm actually going to do this wrong to start off with, to show you that it's okay. So I'm going to choose the wrong choice. Let's say we make, and so don't write this down, but just like pay attention. So we'll make u equal to, let's say, cosine theta. Then du would equal negative sine theta d theta. So d theta would be 1 over negative sine theta du, right? So I have divided by negative sine theta from both sides, and I've just put the d theta over here. And now I'll replace d theta with this. So this becomes sine squared. Oh, I still want to be in blue, so you know that to write it. Sine squared theta. Remember, that's not u. And then times u times 1 over negative sine theta d theta. One of the sine thetas cancels, but now the integral is going to be the integral of sine theta u d, not d theta, du, sorry. And that's not really good for me because now I've got 2 variables and I can't integrate. Oh, the negative, sorry, the negative. Thank you. My body just knows that it's wrong, so it doesn't want to even write the word. Yeah, so negative sine theta u du. There's no way to deal with that because it still has a theta, but we're integrating with respect to u. So we know we didn't do this right because it's not all canceling. So we just go back to the drawing board, and that's okay. We erase it all. And now let's try a different choice. What do you guys think? The other two options that I could think of is either sine theta by itself or sine squared theta. Let's try sine squared. Let's see what happens, right? It might actually work. I'm not even sure. The way I would choose it is I'd choose sine theta, but you didn't know you could just choose sine theta? So, great question. This is actually the way I would think about it, is I'd rewrite this as sine of theta squared times cosine theta d theta. So, and then going back to our typical choices of u, our first choice, something inside of a power. But I do want to let's go over let's go over it again, just real quick. Let's see what happens. U equals sine squared theta. Then du is 2 sine theta cosine theta d theta. Dividing both sides by 2 sine theta cosine theta, you get d theta is equal to 1 over 2 sine theta. I don't think this is going to work out, but that's okay. But let's just see what happens. So you get the integral of u, because u is sine squared, just u by itself, and then times cosine theta, and then times 1 over 2 sine theta cosine theta du. And luckily for us, the cosine thetas cancel, but now we have a 2 sine theta in the denominator that won't go away. So there is a thing called reverse engineered U substitution, which we'll talk about soon, that might be able to solve it this way, but we don't have that terminology yet, so we won't do this, but it could work out. But the correct choice would be U equals sine theta. So I did it twice wrong, and that's okay. I just re-erased it and tried a new thing. It's okay to try and fail. How do you get stronger muscles? Right? You can build like the definition or the tone by doing lower reps and just keeping it the same rep and just doing more and more. It gets you more quote unquote definition, if I remember correctly. I'm not a scientist on working out, but the only way to get stronger is to go ahead and turn it in. The only way to get stronger is to lift larger weights, and sometimes you might fail, right? You might try and pick it up, and it's good. Yeah, that's okay. Yeah. You might fail and then have to go back down. That is okay. But anyways, u is equal to sine theta, which means that du is equal to cosine theta d theta. Dividing both sides by cosine theta allows us to get that d theta is equal to 1 over cosine theta du. You can put the du on top. It's not wrong. I just like to make sure that it's separate because it's not really part of the integrand. So this becomes the integral of u squared times cosine theta times 1 over cosine theta du. And look at that. The cosine thetas cancel. Therefore, at the end of the day, this becomes the integral of u squared du. And that is a nice integral that is purely in terms of u, so we can integrate it. The integral of u squared would be 1 over 3 u cubed plus a constant c. And then now that we've integrated, we can now just replace u with what it is in terms of theta. So this is 1/3 sine cubed theta plus c. Any questions on that? The main goal with doing that stuff and spending a little extra time on it is to just remind us that it is okay to make mistakes. It's okay. Yes, Kate. So we need sine equal to u, sine to the first power. We have sine squared, so that's u squared. that make sense? Still doesn't make sense? Okay, so what we have here is that this is sine of theta squared. Since u is equal to sine theta, this becomes u to the second power. So hence u squared. Is that okay? Paul, yes?
I was gonna ask for a picture of that.
Sure. Can we wait until until the break or after class? Or I guess we just did this. So go ahead and take a picture. So while we're waiting for that, I'd like you guys to try to do the next two problems. Okay. Try to do the next two. I'll slowly fill in details on each. Also, just as a note on 4.5.4 part A, notice that the variable of integration is already u. So you don't want to choose u again. So maybe just choose a different letter. U is just the convention, but you could use B, V, W, H, whatever you want to do. What variable do you guys want to use? K. Sorry, Trevor, I heard K first.
Whatever.
Everybody should be writing something down, trying to write something down. And this way we get Donkey Kong. DK. After these two examples, I'm going to stop doing the division. I'm just going to do it in my head. I know it's a little bit. That's the point. We need to be okay with any variable. But I get it though. I get it. It's weird. It's weird at first. If anybody wants scratch paper, by the way, I've got plenty. And by plenty, I mean like probably 15 sheets. Oh, E to the K. Sorry. See, even I make the mistake. See? I have the answer to part one if you'd like to check your work. If you're still working on it, continue to do so. If we can look at my work to help you figure out the next part of it. But Yes, Alexis.
Yeah.
Yeah. Yeah, I know. And it's coming up, guys. It's coming up.
Well, I thought you skipped it.
No. Don't worry, guys.
Can't wait to be this.
Oh, yeah. I understand that you feel that way, but believe me, like, we're probably gonna have to send some people to the insane asylum because it's gonna be that hilarious. All right, I'm gonna scroll up, but if you need me to come back up to this, let me know. And we'll talk about them after we finish. This year, I'm thinking about it while I'm waiting to write down the answer. Using sine squared theta on the previous example should work, but it requires being very clever. So it does work. It requires doing a little bit of weird algebra. I multiply by t, but you can divide by 1 over t. Remember that dividing by 1 over t would be the same thing as multiplying by t. Either way is fine. Before Alexis asks his question, I wanted to mention something. Like all algebra that we know and love still works here. Everything that we've learned in all of our math classes, all the algebra still works. You can multiply, divide, subtract from both sides if you want to, but that would be actually subtracting would be a bad idea in my opinion. But all algebra still works here. This isn't any new math. It is new math, but it still obeys all the old rules.
I got DT, I don't know how I got there.
Oh.
So, of a DT, and then, so what you have to do, is like, to cancel the T over here, you have to multiply by T. Then that would be canceled. So if you divide by one.
So it's just that the last option.
Did the exact same steps as I did up here, but so.
So you
I mean, is
divide
this mathematically correct though, technically?
up until here it is, this is not.
So.
Yeah.
Okay, but.
Sorry.
I was getting up on the very simple stuff.
And so that's why I wanted to mention this one is like, so this one is a situation where like normally in the last 4 examples or whatever, we've been dividing, but this time we multiply. That can happen. But all like you got to remember the goal is to get the dt by itself. So how like instead of like saying, oh, I just divide, say, how do I get the dt by itself? Here, I would multiply by t to cancel it. But you can still divide by 1 over t. That could still work. It's just remember when you divide by 1 over t, that's flipping and multiplying.
Or you just do this stuff too.
All right. I have the answer up here. If you're still working on it, please do so. We're gonna check back in just a moment. Okay. All right, so let's go ahead. Oh, Sierra, yes.
I wanted to ask if it was relative, but now it's relative again, because you use brackets, and I just don't, I always want to know when do you use brackets?
Ah.
As opposed to parentheses, because sometimes when there's a lot of parentheses, we use brackets, but then other times we use brackets for the area.
Yes.
Something, and then you use the bracket there, so then when do you use the bracket?
Excellent question. So the convention in typed mathematics is to typically always write things with just bigger parentheses. So start with a small parentheses, then bigger, then bigger, then bigger. But in handwriting, that's not very useful. So my usual go-to is, so like I treat the bracket just like it's a parenthesis. It's just a different type of parenthesis to signify new sets of parentheses. So like I usually alternate between parenthesis, then bracket, then parenthesis, then bigger bracket, then bigger parenthesis, then bigger bracket. So that's the way I use it. And sadly, that is a situation where mathematicians would say it is clear from the context what you mean. So if you're seeing it as an interval, you'd see it as 4,2 or 4,5, and that means that it's an interval. That's the sad fact about it. In fact, just as a fun little aside about that, my first semester teaching as an instructor instead of as a TA, I had a student from Romania, and he learned interval notation differently. Instead of parentheses and brackets, it was all brackets, but if you did excluded, this was what you wrote. So in their notation, if they wanted to write 2,5, they would write it as backwards bracket 2, 5 backwards bracket, which looks weird, but it kind of makes sense, right? Because it's not included. I love the notation, but sadly we live in America, the freedom fries and everything. So we use our freedom units. Right? I love it. I love it. I wish we'd change it, but we tried to change to the metric system in the 1970s. Couldn't handle it. Couldn't handle it. It's too much. So asking us to do that would be another big hurdle. Okay, so let's go over these ones again. So a good choice of U would be to choose the inside of a function. In this case, E. So I'm going to make K in this case, but you can use, here's another thing. If it helps you, you can use a capital U. So just instead of doing make your lowercase u's look like this, and then your uppercase u's, you can even make it eccentric. You can make it go really large. It's fine. It's just supposed to be a symbol to represent a variable. Yeah, you can draw a picture. Absolutely. There's a very famous way back in the early stages of the internet, right? When memes were only first being discovered. A person wrote his entire differential equations thing, and he made X equal to a dog, and then Y equal to a squirrel that he drew. And then like he did that, and then it actually all worked out when his teacher said, please don't do that again. So because it was right, it was 100% correct. It's just he changed his variables and it was just annoying to deal with. So you can use whatever variable you want. If you want to use you can use any symbol for a variable. That's what a variable is. It's a symbol to represent an unknown value. Anyways, we made K equal to U squared plus 2U. Taking the derivative of that makes it dk du is equal to 2U plus 2. You multiply both sides by the du, so you got dk equals parentheses. Please put the parentheses on it always, because that entire thing is being multiplied by du. And you probably know what you mean when you write it, but in an exam scenario, you don't want to get slipped up by someone sneezing and you look over for a second. Or in my case, you have a student crying behind you during your final exam. That definitely throws you off. So So du is equal, then we solve for du by dividing both sides by 2u plus 2. So you get du is equal to 1 over 2u plus 2 tk. Replace u, replace your u's with k's. So we get u plus 1 times e to the k over 1 times 1 over 2u plus 2 dk. And luckily, there's a common factor of 2 from that right piece that you can factor out, and then you can cancel the u plus 1s and just get 1/2 e to the k dk. That is a integral purely in terms of k, with the variable of integration being k. So you can integrate that. E is a very, very nice integral. It's itself. So the integral of 1/2 e to the k dk is just 1/2 e to the k dk, or 1/2 to the 1/2 e to the k plus c. Then now that we've integrated, now we replace k with what it is in terms of u. So you get 1/2 e to the u squared plus 2u plus c. Any questions on that one? The next one, a good choice for you would be something in the denominator, but this one has a denominator and then it also has a power in there. So I chose to use u equals lnt. You could try to use it lnt squared. That might work. I think it may work, but you have to do some interesting algebra. But that doesn't mean it's not possible. But lnt is the best choice. So then you get du is equal to 1 over t dt. You want to solve for dt. So you need to get rid of that 1 over t. The best way to do that would be to multiply both sides by t. So you get dt. Dt is equal to t du. I just like to switch it, but you can keep it the same. You can keep t du is equal to dt. However you want to do it is fine. Yes. So we're trying to integrate it. We're trying to find the indefinite integral. Like I'm glad you mentioned that. Yeah, there's a lot of steps going on here, but the goal is to find the integral, to be able to integrate it. Because as it stands, as itself, right here, as 1 over t lnt squared, we don't have a rule that encompasses that. So we're trying to get it digested down into something that we can integrate.
For the area.
Which will be for so in this context, it is just an end, we're trying to find the antiderivative because there's no bounds. But what we can do is we can later use it for bounds. We can do integration, like definite integrals with this as well. And we'll see that I think in 4.6. Is that okay? Does that answer your question? So we're trying to find antiderivatives right now. Yes.
So if we have a power, is it a given case that use
The inside of it?
yeah.
Yes. Whenever I see one of these things, if I've never seen one before, my go-to is to choose the inside of a power. Like if I can, I choose the inside of a power. And if that doesn't work, then I try something new.
Have you ever chosen something from the numerator that was like 2 polynomials, but you chose the numerator as u instead of using the denominator? It's always best to use the denominator.
I can't think of a case off the top of my head, but I'm not gonna say that it's not possible. But it's just I would say probably 9 times out of 10, maybe 99 times out of 100, it's best to choose the inside of a power whenever possible. Like there's kind of a hierarchy. Yes.
From the step from u, the power negative to du.
Here. From here to here. So this is using the power rule, like that we learned in 4.3. So the power rule says that if you have x to the n dx, the integral of that is going to be x to the n plus 1 over n plus 1, and then plus constant c. So provided for n not equal to -1. If it's equal to -1, then you've got the LNU situation. But any other case, even if it's 0.99, use this rule. Is that okay? Yeah, of course. We'll write this in side note land. Thank you for bringing that up. So I chose u, so we get dt is equal to t du. Replace dt up here, replace it with t du. Luckily for us, the t's cancel, and all we're left with is 1 over u squared du. And this gets back to Trevor's question about when to convert it back to the negative. And since this isn't u to the first power, we'll convert it to an exponential form like that. The integral of u to the -2. Then we'll use the power rule. -2 plus 1 is -1. So it's -1 over -1 plus c. And then we can rewrite it as either negative ln of t to the -1 plus c, or if you want to write it without a negative exponent, you could write it as -1 over ln of t plus c. Notice that we don't have absolute values here, by the way, because we weren't integrating 1 over u. Like our u was ln of parentheses t, so we didn't need to replace it with absolute values or whatever. So, all right. So this one here, this was a tough one. And actually, I misspoke, Trevor, because this one's a good one to choose that where I would choose the numerator. So let's try option 1. So maybe you look at this, and you say, well, let's try to use the denominator. There's going to be a faster way, but let's just say for the sake of an argument, you make your u. So option 1. Let's make u equal to square root x. You see the denominator, you're thinking, maybe you space out for a second and ignore the case where you look for higher powers and you decide to just make u equal to the square root of x, right? Then remember, that's x to the 1/2. So du is equal to 1/2 times x to the -1/2 dx. Now, this is a situation where we should convert back to radical form to make it easier to understand. So rewriting that's du is equal to 1 over 2 square root x dx. Is that okay so far? It's not wrong to keep it in exponential form. It'll still work out in the end, but it's just a situation where it might be better to just write it in radical format. How I know that is just from practice. And that's a situation we might need to explore it. If you're still stumped, try looking at it in a different light. That's a very, very classic math move. Classic mathematician move is to say, let's write it in a different way. Maybe that'll make me glean some more information. So then I will multiply both sides by 2 square root x. And I know, technically speaking, the 2 squared x should be on the left-hand side. I know. But I'm running out of space. So we get the dx is equal to 2 square root x du. All right. So then our integral becomes the integral of, remember, u is equal to square root of x. U is equal to the square root of x. So this becomes 5u plus 1 to the 10th power all over square root x, or or u, times 2 square root x du. Now we might be a little bit concerned, right? Looking at this, looking at oh no, it's nothing, the x cancels. But there is. What is u? U is the square root of x. So 2 square root x is 2u. Right? I know that's tricky. Honestly, when I'm doing this for a purpose, to show you something, to show you that you can figure these things out in different ways. You just need to keep working through it. You might want to go back to the drawing board at this point, and that's okay. There is a better choice of u, but anyways. So because it's u is equal to the square root of x, now we can actually cancel those. And now you've got the integral of 2 times 5u plus 1 to the 10th power du. Now, I don't know about you. That's not the joke, by the way. I don't know about you, but I don't want to multiply 5u plus 1 10 times, right? So that might mean that I need to do another u substitution, right? So let's choose another variable. Since we've already used u, let's use another one. Let's just, for the sake of an argument, let's make it w equals 5u plus 1. Remember, the other choice for a good choice of integral substitution is to make it the inside of a high power. So that's what I'll do. Then dw is equal to 5 du. So du is equal to 1/5 dw, right? Dividing both sides by 5. Please stop me if you need me to need a second to digest.
Stop. Okay, I'm done.
Okay, you're good digesting. Excellent. Perfect. So then this becomes the integral of 2 w to the 10th times 1/5 dw. Right? U was 5u of w was 5u plus 1. So the inside of that thing becomes just w, the 10th power, and then du is now going to become 1/5 dw. So that's going to be 2/5 times w to the 11th over 11 plus constant c. I've done 2 steps here. I've combined the 2 and the 1/5 and brought out front. The integral of w to the 10th dw would be w to the 11th over 11. So that becomes now that we've integrated, we can now replace w with what it was in terms of u. So this becomes 2/5 or 2/55, excuse me, because 5 times 11 is 55. 2/55 times 5u plus 1 to the 11th power plus c. But what is u? Way back at the beginning, u is equal to the square root of x. So this is 2 over 55 times 5 square root x plus 1 to the 11th power plus c. And everybody, this is what I like to call a w substitution. That's the joke, guys. Hilarious. Because I used 2 u substitutions, so it was a double u substitution, and the second variable is w. How hilarious is that?
Double dog dairy music make a better joke.
That is the joke, guys. That is the joke. I can sense that you guys are laughing on the inside. So,
It was a joke, and then it made me not want to.
okay, perfect. So, I made that so the reason why so let's elaborate and explain why the joke is funny again, so we can make sure we laugh correctly. So this was a u substitution that required 2 u substitutions, hence a double u substitution, and the variable of my second integral substitution was w. So it's a double meaning there. Oh, I know exactly. That's why I did it. So thank you guys. I will be here for 2 more days. So that's a funny one. Okay, guys. Now, the much faster way to do this. So the main reason why I did this is not the way I would do it.
Yeah. Until it goes.
I did, but more importantly, actually, the real reason why I did it. You guys have a question?
You did the end of your W to the 10th, right?
Yes.
Okay.
Yeah. Because I'm still angry.
Yeah.
It's definitely weird. It's definitely weird to like, we're doing differentiation and then we're doing integration. It's a weird concept. But it's imagine it's doing differentiation with like the choice of u to get you to be able to integrate. But the reason why I did this specifically was not only to tell a joke, but more specifically, it's to say that sometimes it's okay to do more u substitutions. Sometimes that happens. There is a proof that like it's not a theorem really, but I would classify it as a theorem, is that anytime you use 2 u substitutions or more, it can always be done in 1. But the point being though is it's okay to do multiple. You can keep going and then try it again, and maybe you get stumped. And then you go back to the drawing board. A better way, so option 2, which is better, is to make u equal to 5 square root x plus 1. If you do that, notice that is the combination of the 2. That is making, like, this was your first substitution. I need to point it out on the recording so people can see it. in option one, this was the first substitution, then this was the second substitution. But anytime you do two substitutions, you can simplify it down to one if you want to. But it is not wrong to do multiple use substitutions in the same problem. So that was the more implied thing. I just love that joke. But it is possible, and I'd like you guys to do that at home and see how much faster it is. The process here is basically the same at the beginning. You're gonna get 5 halves instead of 1/2. 5 halves times x to the negative 1/2 and rewrite it, but it will get you the same answer. If you're still stumped on that, please feel free to email me out. I'm happy to answer it. I just want to make sure we move on. So now that our funny bone has been adequately tickled, let's move onward. Any questions on that? As an aside, there was so not just my professor at UW, but there was another professor that I worked closely with at OSU, sorry, the Ohio State University. God, I forgot his name at this point. I should know his name. I don't remember. I worked with him. I was TAing for his classes for 5 semesters. I only saw because I only saw him once, 3 times a semester during grading parties. They're not parties, actually. They're not fun. But a grading party, if you ever become a TA, basically they make you sit all together with all the other TAs and grade the exams in one night. They provide pizza, so that's why it's a party. But it's not a very fun party. But anyways, there was a problem on an exam, and I was sitting next to him. The guy never smiled. Never laughed. He was a very, very serious man. And I told that joke, and he laughed. And so that's why it's the funniest joke in the world. Anyways, back to this one. The integral of x squared plus 1 plus 1 over 1 minus x squared. Okay. This is 2 separate pieces. So let's separate it. Because maybe one piece is very, very quick. Maybe it isn't. Or maybe each one will require their own use substitution. That's allowed. But we can't do 2 use substitutions in the same integral, right? Because you only have one variable. So in that case, you need to split it up. So we're going to separate this into the integral of x squared plus 1 dx plus the integral of 1 over the square root of 1 minus x squared dx. And we'll look at each one separately. Sometimes that's very, very useful. Good news is the second one is very quick. You guys remember that one? Very, very close. Sine inverse. Yes. So this one right here is sine inverse of x. Technically plus c, but at the very, very end, we're going to have we'd have 2 constants that will just combine into 1 constant. So we can just wait till the very end to add our plus c. Now let's work with this one on the right-hand side over here. What do you think u should be? X squared plus 1 is a good choice. U is equal to x squared plus 1. That means that du is equal to 2x dx. So what does dx equal? Take a second. I'm not going to write it on the board because I want you guys to get comfortable writing that division. 1 over 2x du. Yes, exactly right. So dx is equal to 1 over 2x du. It honestly feels like one of the most, despite it being quote unquote some simple algebra, it's one of the hardest ones to overcome because it feels like this is new math and you can't do the old math. You can. Everything still works. And I know the way I write it is a little bit weird, but it's for your benefit so that you can look at it and just immediately replace it. Immediately replace it with what dx is. So this becomes then, this second one becomes the integral of x times u to the 1/2. I'm going to rewrite it as an exponential. You could keep it as a square root, but eventually you're going to need to convert it to an exponential anyways to be able to use the power rule, like that x to the n becomes x to the n plus 1 over n plus 1. You're going to need to do it anyways, so might as well just do it now. and then times 1/2x du. And that's awesome. The x's cancel. So we have the integral of 1/2 u to the 1/2 du, and that is an integral purely in terms of u. I mean, like I know you guys were writing down, so slow down for just a moment. So now that we've canceled out those x's, all that's left is an integral in purely in terms of u, so we can integrate it. That's the whole goal of integral substitution, is to be able to cancel, to simplify it down by canceling the small pieces, and be left with just purely u in a nice way that we can integrate based on our simple rules. And this is one of our quote unquote simple rules. I don't mean simple as an easy, I mean as one of the simple cases, the base cases that we encounter. So this becomes 1/2 and then u to the 1/2 plus 1, which is u to the 3/2 over 3/2 plus that constant c. We don't really need to write the plus c actually, because we're going to write the constant at the very, very end anyways, but we can leave it here. However you want to do it. Flip and multiply by the 3/2 becomes 2/3. So this becomes 1/3 u to the 3/2 plus that c. So this becomes 1/3 times x squared plus 1 to the 3/2 plus that constant c. And by the way, just as one more thing, if you want to skip some algebra or some substitution steps, you are more than welcome to do so. If you wanted to go straight from this step to here, be my guest. If you want to go from the integration and immediately replace it, like do the integration in your head and replace it with x's, that is fine with me. That is still 100% valid. That is just the quick way. It's just there's more chances to make a mistake if you're doing it all in your head. You know what I mean? So that's just the thing. Any questions on any of that work? Okay, to have questions. This is something completely new. Just to vent for like to rant for just one moment. No. One of my least favorite things about so I learned calculus in a quarter system, and the way you learn it in the quarter system is it's broken up into 3 sections. There's differential calculus. So the first quarter purely focuses on differentiation. You don't touch integration at all. Second semester is purely on integration. And then the third semester is multivariable. Whereas here it's first one is integration and differentiation, like the basics of differentiation. Whereas it would make way more sense, in my opinion, to just add in more to this, more applications of derivatives, and then wait until the next semester to purely cover integrals. One day I might try and talk to all of NC to try and change that, but alas, I am just one instructor out of hundreds of instructors in Nevada. So I just wanted to rant on that for a second to like say, I understand your frustration here if this is feeling weird, because we've been differentiating for 13 weeks. And now we're learning this new thing called integration. It's very frustrating because they're opposite but connected. So anyways, we found our integration. So we're good to rewrite everything. So we got 1/3 x squared plus 1 to the 3/2 plus sine inverse of x plus our constant c. And that is our answer. Okay. Ooh, that's right. I added this one. Okay. So we'll start this one off together and then we'll move from there. What do you think for part A? Go answer out loud. What do you think you should do for part A? The ln of tangent theta? Or just the tangent theta? Excellent thought at first. Excellent question, excellent point. So sadly, it won't cancel. Because remember, this like the sine over cosine, that's on the inside of the natural log, so it won't cancel with those things because it's well, you could split it apart into two pieces. Is that what you're talking about? Like a natural log of natural log of tangent of theta. Yeah, you have to take everything because natural log by itself doesn't like it needs to have a variable inside. So tangent theta would be a good option. It's not the right option. And that but I'd like you to we're gonna go through it together. U equals tangent of theta. It's close to the right option, but it's not the right option. So you can still do it, but you're going to require more. So then du is equal to secant squared theta d theta. And looking at this, I'm a little bit worried because secant squared theta, I don't have any. But remember, secant squared theta is 1 over cosine. I saw 1 over cosine squared theta. So this is really 1 over cosine squared theta. So to solve for d theta, what should I do? Multiply by cosine squared theta. So d theta would be cosine squared theta d theta, or du. So this becomes the integral, still not in the correct format. It's the integral of ln of u divided by sine of theta, cosine of theta, times cosine squared theta du. Now here's where things get interesting. If you can solve it this way. You guys want to see how? Kind of. So, I mean, yes, you will, but you have to do something very, very interesting at first. One of these cosines will cancel, right? So then you have the integral of ln of u times sine of theta times and then cosine theta up top du, right? So cosine over sine is cotangent, but cotangent is 1 over tangent. So this right here is putting a tangent on the bottom. So that's ln of u over tangent of theta du. But what is tangent of theta? It's u. So this becomes the integral of ln of u over u du, and then we'd need to do a we'd need to do a second integral substitution, making u a w ln of u, and that will work out. But that's a lot of trickery. That's a lot of cleverness to it. The better, and so whenever you can do double, like 2 integral substitutions, you can simplify it to 1. So this is one option. It's not wrong. It's just it requires being very clever for a second and being okay with having a mess. It's okay. It's like having a toddler. You had to be okay with just chaos. So the faster way. And so, wait. What I'm going to do is I'm going to erase this for a second and just say you get to this point. You notice that you didn't get everything canceled. So you're like, that's not good. So let's go back to the drawing board. Let's go back to the drawing board. Let's try something different. It's okay. We didn't fail. We just learned a way to not do the integral. That's all that happened. We just learned a way to not solve this problem. There's plenty of problems in the world. Sometimes we don't solve them right on the first go. That's okay. So a better option, looking at this, I'm a little bit perplexed. Because I go through things in my head when I'm doing these types of problems. Honestly, this is one actually, just true story. When I was I had this one this semester before this semester started. I had this one because I saw it somewhere and I was like, what do I choose? Because I originally started with trying to choose tangent theta and that didn't work. I mean, I found the right way, but by doing that, by being okay, just kind of messing with stuff. But then after a while, I was like, okay, let's try different things. It's like, what if I made u equal to sine theta cosine theta? But then that would require a product rule when I take the derivative. So then I get sine theta times like f prime g, so I get cosine squared theta minus sine squared theta. That's not going to get me anywhere. I can make u equal to sine theta, but that's not going to get me anything to make that ln of tangent theta any prettier, right? I could try making u equal to cosine, but I run the same situation. So what am I to do? I've tested each individual piece. I've tried this, I've tried this, I've tried this. So what? A whole numerator. That's another option. It could work, it could not work. We don't know. Let's find out. Let's try. In the words of Sesame Street, I wonder what if. Let's try. All right. Everybody does. It's a classic thing they say in Sesame Street. I wonder what if. Let's try. It's in newer Sesame Street. Say what? It's on HBO Max right now. But actually, they still PBS Kids is still free. The app is still free. So this one's a little bit scary, but remember, all our rules before, they still apply here. So taking derivatives, we're still going to follow chain rule. We're still going to follow product rule. We're still going to follow quotient rule. All those things are still in play. So du 1 over tangent theta times the derivative of tangent theta, which is secant squared theta, d theta. And we look at this and we're like, uh-oh, this doesn't look good because there's no sines and cosines. But remember, whenever it comes to a trig problem, remember that you can rewrite trig in a million different ways, right? You can write sine squared as 1 minus cosine squared. You can write it as 1/2 sine theta, sine 2 theta, right? Something like that. I can't remember off the top of my head, but like you can write it in a million different ways. So always be open to rewriting these things in different ways. Tangent theta, this is the same thing as writing du is equal to, tangent is sine over cosine. Since it's 1 over tangent, that becomes cosine over sine. Cosine theta over sine theta. And secant squared theta is 1 over cosine squared theta, d theta. So one of the cosines cancels. And so we've got du is equal to 1 over sine theta, cosine theta, d theta. That's looking better. And we're feeling better about this. If this was an integral on my exam, and I was taking the course with you guys, I guarantee you, I probably would have stopped at du equals 1 over tangent theta secant squared theta d theta, and I probably would have tried something else. And then I would maybe, that's not working. So maybe this is the right choice. I've exhausted everything else, and those ones never cancel things. Maybe there's something else here, and then I would continue onward. Talking about this idea that math, like being a good mathematician means trying different avenues and then coming back to to old avenues to see if you can glean new information. Because maybe that was the right path. You just didn't see one piece of information. So how do I get d theta by itself? Multiple both sides by sine theta cosine theta. So d theta is equal to sine theta cosine theta du. So this becomes the integral. The numerator, we chose the whole numerator to be u. So this is u over sine theta cosine theta times sine theta cosine theta du. And all of that cancels. And now we're getting somewhere. Now we've got the integral of u du. Very, very nice integral. Because the integral of that is just 1/2 u squared plus c. So that's going to be, once we replace u with what it is, 1/2 ln of tangent of theta quantity squared plus c. And so you, Sierra, you asked about like when to use parentheses. I have my own little flair on it. I think every mathematician kind of uses their own thing. If the parentheses belong to a trigonometric function, the next set of parentheses I will use to be parentheses again, and then I'll start using brackets. But that's just me. It's just my own little thing on it. My own little signature. But basically any choice of grouping symbols will be fine. This one was a really hard one. Yes, Paul. Ln tangent of theta. But a pretty fun one. I think this one's cute. It's very, 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 very clever. You don't think that's cute?
The box makes me think Cox and Bell, or
Where's that from?
guy I used to watch on YouTube, Math by Five.
I think I've heard of that YouTuber. That's right. That's right.
But if it, like he does that, he solves the answer with Cox and Bell.
Huh.
Like it,
I love it. I like. I should watch him. I need to get some.
still like, I don't know, he's funny. He goes, okay, so then this we're gonna do. Because we go everything.
All right. We all good? Do you guys have a question, Kate and Julie?
Wow. Where did we get the 1.5 from?
1/2 u squared?
Yeah.
Because I'm taking care of the integral. It's you like as it stands right now, it's just an integral. So I'm finding the antiderivative. I'm not like you use differentiation to be able to integrate. So it's like first take derivatives, then integrate. First take derivatives, then integrate. All right, this one here. This one here. This is two separate u substitutions because we need to split it apart. This is the integral of cosine of ln of z over z dz plus the integral of e to the 5z dz. And I'm doing that because I know each one of those ones should, like, whenever you see multiple terms, it's probably a good idea to separate it and look at each piece separately. If that doesn't work, then try again with combining them. So it's a situation, look at it different ways. If when you separate it, it doesn't work out, then try combining it. But 9 times out of 10, you should separate it first. Oh, because it would make it e to the z. Ha 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 ha. Love it. All right. So let's just do the first one off on the side here. Let's call this piece 1 and this piece 2. So 4, 1. Should I stick with green here, like in writing the whole thing, or should I go back to black? It's your call. Just keep it green? Okay. So you get the integral of cosine of ln of z divided by z dz. And by the way, I'm just checking back in. Am I writing down stuff too fast in this section? It's okay if I am. Please let me know. It's okay. If you need me to slow down, that's totally fine. Integration is probably one of my favorite topics in mathematics and favorite topics in calculus specifically, because integration has so many, like it's your first start in answering the question of no longer, these are the rules, find the answer. It's which rule should you use to find the answer? That's the new extra added step in mathematics. What rule do you use now? So what do you guys want to use for u? The whole numerator might not be the best call because then you'll have a sign with your derivative. Like I love the idea. So I want to do that off on the side for just a moment. If you make u equal to cosine of ln of z, then your du will be a negative sine of ln of z times 1 over z dz. And the problem there is that like even when I solve for it, I'm sadly not gonna be able to cancel. Like I'm still gonna have a cosine. There's not gonna be a way to cancel that sign. Does that make sense? So great idea to start with, but as you start doing this more and more, you don't even need to try and plug it in to figure out that it's not going to work. It just takes time. Be okay doing the algebra and letting it go and go from there. But one of the good options is always to choose the inside of a function. So I would recommend making u equal to ln of z. So then du is 1 over z dz. So to solve for dz, we will multiply it by z. So we get that dz is equal to z du. So this becomes, when we got a second, and I've mentioned it several times throughout this semester, but please remember, do not be discouraged if you didn't see it right away. I've been doing this for a very, very long time. So I can do this very quickly in my head because I have done it for so long. Just like it takes a long time for a first grader to know what 1 plus 5 is, but we know it's 6 immediately because we've done it for so long. Yes, Paul.
You blindfolded?
This problem?
Yeah.
Probably.
Put your hands-
Well, not with my hands tied. I can't write with that, but I probably could do it with I mean, it would be all over the place because I can't know where I'm writing, but so u is equal to the natural log of z. So this is cosine of u divided by z times z du. The z's cancel, luckily for us. So this is the integral of cosine of u du. And we know what this, so this is an integral purely in terms of u. So we're good. We've gotten rid of all of the z's and we're only with u's. And so we can integrate it. What is the integral of cosine? Positive sign, because derivative of sine is cosine. I have to do that every time. I do not have my cosine and sine integrals memorized. I have to do it every time. I have to check myself every time. So this is sine of u. And then we can write plus c, but we're just going to combine at the very end. So we'll just write it this. So sine of ln of z. We'll write the plus c at the end. Any questions on part 1? For 2, we have the integral of e to the 5z dz. There's only one option to choose. The 5z. Yes. And this one gets to a, so u equals 5z. So du, what is du? dz will be 1/5 du, but like you're getting ahead of us. Excellent, excellent. But du is going to be 5 dz. It's okay for our dz's to not have a variable in them. That can happen. So dz is equal to 1/5 du. So this becomes the integral of e to the u times 1/5 du. But the integral of e to the u is itself. So this becomes 1/5 e to the u plus, or we'll leave the plus c until the very end. And then that's 1/5 e to the 5z. Right here,
The du, yeah, I didn't see that.
du equals 5 dz.
Yeah, I was
Yeah.
confused on the d.
Oh, for sure. Sorry about that. So now we have both integrals. Let's combine them and write our answer. So the answer is going to be sine of ln of z plus 1/5 e to the 5z plus that constant c. I like to call that, by the way, my consistency. Because it's consistent every time. That's a better, that might, there we go. Thank you. That's a better joke. That's a better joke than the other one. It was making her very dizzy.
It's a better joke because you didn't tell us it's a joke.
Okay. Let's see here. How much do we have left? We have this. Okay. I want to go over reverse engineer to use substitution. This is like, we've already covered so much with regards to these other things. I don't want to get us a new method yet. I'm going to leave that for next time. But I do want to say this one right here, you're going to encounter this hypothetically a lot in like depending on your teacher. It shows up so much for whatever reason in 182. And it's going to get to the point where we don't even need to do a use substitution. So right here, I have a bunch of rules for us. So let A and B be constants. So all of these ones, you can do them immediately. Cosine of AX plus B. So if it's just a linear term, like 5x plus 7 or 3x minus 9 or 18x plus 1/2, doesn't matter what it is. If it's a linear term on the inside of one of these nice functions that we know so much about, it becomes immediate. It becomes, this one will be 1 over A sine of AX plus B plus C. So you can use these formulas without, as fact. You don't need to do any integral substitutions for these. The substitution, to verify it, all you need to do is make U equal to AX plus B. Then du will equal A dx and so on and so forth. But so you don't need to do it for these ones. You can just immediately write the answer. Hopefully your teacher isn't a stickler about this in 182 and doesn't make you do that, because that's just cruel. That's like making your students try and like show that 1 plus 1 is equal to 2. It's very, very annoying. E to the AX plus B. 1 over A, E to the AX plus B, plus that constant C. For the same reasoning, U will equal AX plus B. The derivative of that will be du equals to A dx. And that's where you get that 1 over A. Sure. That's where those rules come from.
What are those random dots under?
Dot to mean like fill out the rest of it. Draw the rest of the owl, if you know the meme. If you don't know that meme, just search draw the rest of the owl and you'll see what I'm talking about. It's an old meme, sir, but it checks out. That's another old meme. Never heard of it? Does anyone know what I'm talking about when I say that meme? No? Okay, I'm getting older. Excellent. Okay, so it's always just 1 over the coefficient in front of the x term and then just repeat it. So this one here, 1 over AX plus B. You don't need to do, this is the main one. This one, because there's a thing later in 182 called integration by integration by partial fraction decomposition. Mainly they just call it integration by partial fractions. And a lot of times you get something like 1 over 2x plus 5. And it's just, those ones already take so long that like, it might be just nice to just know this rule. So it's 1 over A natural log of absolute value of AX plus B plus the constant C. So here are some examples of how to use this once you've written them down. All of them have the same proof for this formula. So now you can use these without as fact. You don't have to prove them. You don't have to do integral substitutions if something like this shows up. But remember, this is only for linear terms. If it's AX plus B, AX to the first power plus B, any other time, it won't work. So 1 over 3x minus 2 is going to be 1/3 ln absolute value of 3x minus 2 plus C cosine of 7 theta. That's really 7 theta plus 0. So it's going to be 1 over 7 sine of 7 theta plus c. So instead of writing all that u substitution stuff, you can just write the answer. Please do so if you can. Remember these ones. It's not going to help you too much in this course because we're still learning u substitution. So it's not wrong to use u substitution, but later on in your career, if you decide to take 182, it'll help you out, especially during partial fraction decomposition. So that's all of 4.5. Now, so we'll come back, like once again, we'll come back to reverse engineer the u substitution tomorrow on Wednesday, because I don't want to overload you guys with too many new techniques. We've been practicing u substitution. Let's practice that first, and then we'll talk about reverse engineered. But for now, I'd like to go ahead and do the 4.6. I'd like to do these ones, because now we have rules for the integration of all of trig sub. So the integral of tangent, how do we find that? So what function would you have to take the derivative of to get tangent? Because the derivative of tangent is secant, but the derivative of secant is secant tangent. So
1 over cotangent.
1 over cotangent might be a good start, but one of the things you should always try and do, maybe if we write this, I'm going to tell you that the answer is that it should be ln of, oh God, I can't remember off the top of my head. What is it? It's either ln of negative ln of cosine. Oh no, it's ln absolute value of secant theta, or secant x plus c. And the reason for that, proof. If you make let's rewrite the integral. The integral of tangent x dx is equal to the integral of sine of x over cosine of x dx, right? And that's something that we can look at and we're like, okay, well, a good choice of u substitution would be the denominator. So we'll make u, and then I'll put or negative ln absolute value of cosine. Like the typical convention is to write it as natural log of secant of x plus c, because then you don't have to deal with the negative sign. But negative ln of the absolute value of cosine of x plus c is how we get the formula. So if we do this, then we'll make u equal to cosine of x, so that du is equal to negative sine of x dx. And then that means that dx is equal to 1 over negative sine of x du. So this becomes the integral of sine of x over u times negative 1 over sine of x. Or let's just leave it as how I wrote it. 1 over negative sine of x dx. So that's going to be, the signs cancel, but don't forget about that minus sign. So this is the integral of negative 1 over u du. Oh, that shouldn't be a dx, that should be a du. I'm sorry. That negative sign sticks around. We got 1 over u. Absolutely, so that would be the negative natural log of the absolute value of cosine of x, or negative ln of u So value of u plus c, which would then becomes negative ln, the absolute value of cosine of x plus c. And the reason why we say secant, by the way, is by the properties of logarithms. So let's think about that for a second. Let's make sure we understand this portion. Does anybody have any questions on this? This is a lot, guys. So I'm thinking about, and like I'm gonna write down the other rules after this, and I think I'm gonna call it good. I think we've had enough information for today. So we're gonna write down the rules after this, and then we'll go from there. So naturally, the reason why it's natural log of absolute value of secant is because imagine this is a -1. So this is equal to natural log of the absolute value of cosine of x to the -1. But this is 1 over cosine of x, which is secant of x. That's the reason why. And that the only reason why we write it as natural log of the absolute value of secant is so that we don't have to write a negative sign. It is completely valid to write this as negative natural log of cosine of x. But it's just the convention is to write it as natural log of secant of x. Does that make sense? Despite it, like, you don't have to prove this now. This is a formula that you can use. The integral of tangent of x is natural log of secant. Now, this one here, this one's ridiculous. You would not be able to guess it. If anybody knows it off the top of their head, has a good guess that gets it right, I will give you $100. Close, but no. It's actually the natural log of the absolute value of secant of x plus tangent of x.
Give them $50.
I'm gonna buy this in it. And if you want to know the reason for it, it's probably one of the most ass-backwards discoveries I've ever seen. I think what happened is someone took the derivative of this and noticed that they got secant theta, and then they were like, okay, that's the formula then. So like they took the derivative of this function to find the antiderivative on accident. I think that's what happened because the trick, if you want to prove this in your own time, I think it'd be hilarious. It's a good problem to hang out with the bros and do, is to multiply the integrand by secant of x plus tangent of x divided by secant of x plus tangent of x. And the reason why you have to do that is, remember, that's technically multiplying by 1, which is the only way you can do something with an expression. You can only multiply by 1 or add 0 and stuff, and then and make u equal to secant of x plus tangent of x. If you do that, this will fall out. It'll be nasty, but it will work. So definitely give it a chance. If you're really bored and you have nothing else to do while you're studying for finals, right? Like instead of like, doing something to keep yourself relaxed, like listen to some calm music, doing a Sudoku, do this problem, it'll calm you down right away. Sudoku is a very relaxing thing, at least for me. So that's that one. And then the other two are the good news is they're very, very symmetric. So the integral of cotangent is the natural log of the absolute value of sine of x plus c, and cosecant is natural log of the absolute value of cosecant of x minus cotangent of x plus c. I just find this very fascinating, and it just speaks to the true beauty of trigonometry, that even after using different, even after calculus, trigonometry still stays pretty nice and pretty. Just another reason to appreciate trigonometry for what it is. Okay, so now, by the way, you have all the trig formulas here. Not trig formulas, all the integral formulas right here. So the quiz on Wednesday will only cover this stuff. It won't cover reverse engineer use substitution. So expect basic use substitution, nothing crazy. And then indefinite integrals for the most part.
What section would it cover?
So don't worry about 4.1 and 4.2. So 4.3, 4.4, and then 4.5. Yes, I'm gonna send out an email soon. And so with my
And what we just covered in 4%.
yeah, in 4.5, yeah. So nothing in 4.6. So you don't need to worry about memorizing these formulas. These formulas will not be on there. Okay, so I'll send out an email soon. If you guys have any questions, please feel free to ask. Otherwise, you guys have a great rest of your day. If you didn't turn in your exam redos, please turn them in now. Yeah, I'm gonna put that like when I get to my office, as long as nobody's there, I will be putting it up. But it will be up by tonight, no later than that. And if it isn't, send me an email, an angry email telling me to do it. Yeah, you can just put it right there, or you can attach it to yours. I've got a stapler here. Either way is fine.
Take the physical copy, Mike.
Sure. Right, yes. There you are.
Have a good day.
Thanks, you as well.
Take a picture of those first two problems.
Yeah. Oh, let me turn